इसको चालू करो। हो गया ना? So good afternoon and welcome to advanced NMR spectroscopy course. Today I will tell you how to solve some of the problems or how to solve problems whatever I taught in module 3. I'll just keep a representative example only, and then I will give you one assignment. Maybe by Wednesday you will get the assignment. Okay, so before I start anything, there is a correction in slide number 14, okay, in lecture 70. Okay, so you please note down this. So only the difference is here that I said that delta nu was equal to nu A minus nu B, when nu and nu B are the chemical shifts in hertz of species A and B at coalescence. But at coalescence, delta nu is 0. Okay, so actually it will be the difference of chemical shifts in the slow exchange regime. Okay, so that is the only difference. Okay, otherwise everything will become 0. Okay, and also I have introduced that not necessary you can find out the rate constant at any other temperature if you know the chemical shift difference at that temperature. So this is the chemical shift difference in the slow exchange regime. This is the chemical shift difference at a particular temperature, and then automatically you can find out. We will see some examples. One example, at least I think I have this problem. Okay, so please note this is very important. Okay, so now this is again a molecule. This is called bulvalin. Okay, so this is the structure of the bulvalin. So if you see that this molecule is actually continuously undergoing a chemical reaction called Cope rearrangement. Okay, Cope rearrangement is nothing but 3,3 sigma atomic rearrangement. Okay, so there is a continuous bond reorganization is taking place. See this cycle, you can see this in this structure, the cyclopropane ring is here, whereas in this structure it has moved to a new position. Okay, so similarly, there is another position is also available between this hydrogen, and this carbon. Okay, or this carbon, and this carbon. So there are all kind of possibilities are there. Okay, so this is but the reaction, the product, because there is no change in the product structure, so that's why you cannot see any difference in the structures. Okay, now we'd like to find out this by dynamic NMR spectroscopy. Okay, so first, before doing anything of such structure is given, now you have to find out what are the different chemical environments of all the protons. So the best way is to find out the first thing is to find out whether there is any symmetry element present in this molecule. If you see very carefully this molecule, what type of, so the first question is what axis of symmetry this unique structure has. So you should be able to find out whether there is any such symmetry axis is there or not. Okay. Okay. So now let us see that. And okay. So then I have shown you here the dynamic NMR spectroscopy, a temperature dependent spectroscopy. So when you record the spectra of this molecule, okay, at minus 85 degrees centigrade, you see actually there are 4 sets of. So if you want to know this, what will be the symmetry axis in these molecules? The molecule is having a C3 axis. Okay, I'll show you that C3 axis. Okay, so the molecule possesses a C3 axis of symmetry. What is that C3 axis? So it is passing through this. So this is your C3 axis. Okay. So that's why you'll see if there is C3 axis, this hydrogen, and this hydrogen, they are chemically equivalent. I'm talking about chemically equivalent. Okay. And then you will see that this hydrogen, and this hydrogen are also chemically equivalent. And this hydrogen, and this hydrogen are chemically equivalent. And you will see, and this hydrogen is separate. So there are 4 different groups of proton. Okay. Now, if you see, now I have told them chemically equivalent, but you will see that coupling constant of this proton with this hydrogen, and this hydrogen are not same. So they are chemically equivalent, but they are not magnetically equivalent. Similarly, this one, you will see the coupling constant with this, and these are different. Okay. Similarly, this one. So what you will see that you will get a H. I will give H A prime, H A double prime. Similarly, you will see that these are also, if this as HB, it will be HB prime. Same thing, if this coupling, if these coupling constant are not same, you will see that they will also have different coupling constant, and this will also be B double prime. And then you will see that this is C prime, this is C double prime, and this is D. So this is nothing. So what is the popular nomenclature? So you will have, so according to the popular spin system, the nomenclature of this molecule or spin system will be A prime, A double prime, B prime, B double prime, C prime, C double prime, and D. Okay, so the answer is popular spin system is this. Okay, similarly, all these carbons are also different. So all the carbons, see, even this carbon, they are also different. Okay, so they have also the same popular spin system. Okay, I have already labeled the proton, so you can same labeling you can give to the carbons also. Okay, so whenever there is such kind of structure, I ask the NMR and dynamics or whatever, your first job is to find out if there is any symmetry axis present, whether any plane of axis, plane of symmetry is there, axis of symmetry is there, or center of symmetry is there. So okay, in this molecule there is only a C3 axis. Okay, and then you should see whether the protons, you have to see the chemical, whether the protons, which groups of protons are chemically equivalent. Okay, after doing that, you should see how their couplings are related to different protons. If you see the same chemically equivalent protons have different coupling constant to the protons of other group or other proton, then they will be magnetically non. Okay. Okay, it's clear. So you first see the symmetry axis. Okay. Then the chemical equivalency, and then you see the magnetic equivalency, and accordingly you give the name of the spin system. Okay, and then you should label all the protons and all the carbons as per popular spin system nomenclature. Now, the spectra, what I was showing you here is that at minus 85 degree, you can just try to you just try to see that the changes it is happening when going from minus 85 degree to plus 6 degree and then plus 15 degree to 120 degree. What you the changes you see. Let us just try to remember that a picture of it, and then we'll see. So now I'm telling here that at minus 85 degrees centigrade, nothing extraordinarily occurs. Okay, and the 100 megahertz one-eye spectrum shows 4 complex multiplates. Okay, so although there you see two multiplates, this is one, and this is actually there are two, you can see, but here somehow it has merged. So there are also two multiplates. And there are also two multiplates. Okay, and there, because we have seen the molecule contains 4 groups of protons. So you will see 2 groups of protons are here. And mostly it is the chemical shift, say you will come to know it is coming between 5 to 6. So here the alkynyl protons will be there. And here you will see the aliphatic protons. So mostly it is the HD and those HA prime, H and H A double prime, the cyclopropyl protons. Okay, now let us go there. Okay, center is 2.07, 2.13. So these two multiplets are merged, and then 5.62 and 5.70 they are overlapped. Okay. Now you see that identify the group of protons. Now if you see this molecule, the most uphill shift, chemical shift of the protons will be these cyclopropyl protons. And they are, as I told you, they are chemically equivalent, so they are coming at the same place. So these two delta 2.07 HA prime and HA double. Okay. Now you see the 2.13. It will be the sole this proton, only this proton. So it is the HD proton. This is there. If you remember that I will give the nomenclature HD, and then you will see that HB will be slightly uphill than the H. So if we put these are HB group, these are HC group, HB protons will be slightly uphill due to the anisotropic effect. Anisotropic effect of cyclopropane. So anisotropic effect of cyclopropane, we have seen that it shifts moves the nearby protons and carbon to higher or moves uphill. So out of these two olefin, so this will come. So delta 5.62 corresponds to HB prime, HB double prime. So and delta automatically the remaining, the delta 5.70 is HC prime and HC double prime. So this will be your answer. Okay. Now next question is, as the temperature of the sample raise, now we are increasing. You have seen the okay, the multiplates broaden, okay, and move together. Okay, if you see the spectra, you see they are now moving. Okay, they have become broad and they are now moving towards each other. Okay. At 15 degrees centigrade, the spectrum coalesces. Okay, both the peaks merges. Okay, both the multiplates merges. You can see at a 15 degree it merges. Okay. And you can see the width of the signal, 150 hertz, is so broad. So then what is this called? This temperature at the temperature when you get the two peaks merge each other or coalesces, okay, with a very broad peak. What the temperature is called? It is called TC, okay, or temperature of coalescence, okay. Okay, so that is the answer. Okay, straightforward. Now, next question. Okay, for the same problem, at 120 degrees centigrade, there is one sharp singlet. Predict the chemical state of the pulverin at this. So now this is at the first exchange limit. Okay, so what will be the chemical state? Okay, so if you remember that any NMR parameter P will be equal to summation of P is equal to summation of Pi. Okay. If you remember. Okay, so here our NMR parameter is the delta value. So delta will be equal to, now you see the, so you have to find out what is the, so there are 4 groups of protons. So the first group of proton is your, that is the 3 proton, and the chemical shift is, if you remember, 2.07 ppm plus 1 proton into 2.13 ppm plus there are 3 protons into the B group of protons 5.62 ppm plus 3 protons of 5.70. Now how many, so how many total protons are there? 10. Okay, so it will be weighted average of the chemical shifts of all protons. It is nothing but the weighted average of the chemical shift of the all protons. So total protons are 10 and these are the chemical shifts. So if you do that, you will get 4.23 ppm. So your delta, okay, in the first regime, okay, and that only you see, you can see that it comes around that position. This is around 4 point, you can see clear. Okay, so that comes at 4.23 ppm. Now we are recording the NMR at, proton NMR at 100 megahertz. Okay, so if you record the carbon 13, what you will see? What will be the NMR frequency of carbon 13 in the same machine? It will be the 100 into the gyromagnetic ratio of carbon by gyromagnetic ratio of hydrogen. So this is nothing, almost it is about 1/4. So that's why it is 25 megahertz. Okay. Okay. So that's why I'm telling it is 25 megahertz, proton decouple. So we are doing a broadband decoupling. I think that you have already heard from, I have also told, as well as Professor Hosur has told, what do you mean by broadband decoupling. Okay. A bulbalin consists of signals. So how many different groups of carbons are there? There will be also 4 groups of carbons. This is one group. Where that, okay, then this is another group, this is another group, and then the soul is this one, the 4th group. Same, you will see only 4 signal, 21.0, 31.0, 128.3 and 128.5. And if you see the analogy, the most upfield carbon will be the cyclopropanes. So you will have these cyclopropanes. I'll put them. I have put them as A group carbons, A, C A prime, C A double prime, delta is 21.0. Okay. Then CB prime, CB double prime, delta will be B is this. Okay. So that will be your 128.3. Okay, because those are olefinic carbons, alkynyl carbons. Okay, and this out of these two, this is slightly uphill again due to the cyclopropane system. Okay, then you have CC prime, CC double prime. That is again alkynyl. So delta is equal to 128.5. So this is your A. I will put A. These are all B group. These are C and this is D. And then finally the carbon D delta is 31 point. Okay. Here, so we could identify all the carbons. Okay. Now, the next question in the same problem, which will coalesce at the higher temperature, the 100 megahertz proton NMR spectrum or the 20 megahertz carbon 30 spectrum. Okay. So how we'll find out that? Okay. So what you have seen, maximum proton, you see what is the maximum? Maximum delta 0 for 1H is how much we have seen? 5.70. You see the 0 minus 2.07. So 2.07 are these and 5.70 are these protons. These protons are most downfill and these protons are most upfill. So that becomes, okay. So this is in ppm. Now, as we know, all these things you have to do it in hertz because we will be getting the rate constant, na? Okay. So into 100. So this will be in ppm into 100 hertz by ppm. So you will get ultimately in hertz. So that gives you, if you do the calculation, you will get 363 hertz. Okay, there may be a fraction, maybe decimal point will be there that you can put it. Okay. Now you see for carbon 30. For carbon, okay, is what is the value? So that we saw is your 128.5 minus lowest one or something 21. This will be in ppm into 25 hertz by ppm. And if you do that, this you will see 2690 hertz. Okay. Now this clearly tells that the carbon 13 will require higher temperature for coalescence. Okay. Because the coalescence temperature is directly proportional to the del delta. Okay, if del delta is small, you increase the temperature slightly, you will see the peaks will merge. But if these peaks are quite far apart, you will see that. So that's why when if you record a proton NMR, you may see that the peaks have coalesced, or you got the proton peaks have merged together. But still, if you record the carbon 13, you will see the carbon 13 peaks are coming separately. Okay? Because they have a different coalescence temperature. Okay. So the carbon 13C from or you can write Tc of carbon is greater than Tc of hydrogen. Predict the 13C chemical shift of fast exchange spectrum. So exactly the same way what we did for proton, you have to do it for carbon 13 also. So the average chemical shift of 13C peak under fast exchange will be delta C is equal to exactly same. So you have 3 carbons having chemical shift of 21.0 plus you have 1 carbon whose chemical shift is 31.0 plus 3 carbon whose chemical shift is 128.3 plus 3 carbon whose chemical shift is 128.5. Now how many carbons are there? 3. Like exactly like protons, the weighted average of all the chemical shift of carbon, and if you do that, you will get a single peak. That means if you heat the sample to a higher temperature, okay, it will not be the temperature. You see in this proton NMR, you might have seen that at 120 degree, all the protons are coming as single peak. But in carbon 13, you may not. You have to calculate. Okay, one can calculate. Okay, the formula is there. Okay, you can find out. Okay, so what will be the at what temperature this you will get the carbon 13 peak as a one. One can calculate. Okay, you should try that. Okay. Now I have taken a very similar example. Now you will see that, okay, the same things I have explained in this. Okay, so this is the NMR spectrum of NN dimethyl formamide. We call this as a cis-methyl. This is trans-methyl. Okay, and we know that they come different. So you will see that the cis will be this will be your cis, this will be your trans. Okay, because this is anisotropic deshielding by the carbon. Okay, and there is a restricted rotation due to N lone pair and C double bond O resonance. Okay, so this makes this partial double bond character of this bond. So that's why this rotation along this single bond is slow at room temperature. Okay. And if you increase the temperature, you see that the fastest lines will become broad, then become very broad, and then they coalesce. Okay. And then if you heat further, you will get a sharp line because now the rotation is so fast in NMR time scale, you are getting an average of these two lines. Okay. And we know the population of these two, population of this PA and PB are equal, 0.5, 0.5. Okay, because there are two methyl groups. Okay, now you see the question. At 250 megahertz, the proton, one each of methyl groups of DMF appears. I have given the chemical shifts, and 13C value is also given. Okay, in the slow exchange regime, means in this condition, so this will be 2.74 and this is 2.91. Okay, and the carbon 13 for this is 30.1 for carbon, and this is 35.2. Okay. Now calculate the rate constant at Tc for the protons. You have to find out the rate constant. Now, which formula I will use? Okay. So now that so we have to now if you remember that I have to given the formula K coalescence equal to, in fact the very first slide I did the correction, it is 2.22 del G. Okay. So here you can find out that delta 0 is equal to, for proton it is 2.91 minus 2.74 ppm into 250 Fards per ppm. So that if you do it, it becomes 42.5. If you subtract and then multiply it by 250, you will get 42.5. Okay. And so nothing, 2.22 into that 42.5. So the rate constant will be 94.35 per second. Okay. Because hertz is nothing but per second. Okay. So the rate constant is per second. Okay. So you can find out for carbon-13 also. Okay. So for carbon-13, then you have to see the 250 megahertz will not be no more 250 megahertz. It will be different because you have to, it will be 1/4 of that. Okay. Now the next question you see. The sample is now heated to a particular temperature and the two proton brought signals with a separation of 30 Hz. So you go to this situation. Now we are bringing a situation like this. Okay. So see the separation between these two and these two will not be same. If you keep on increasing the temperature, their separation will decrease. Okay. So that's why now this is 34.0 Hz. Okay. Calculate the K value for that. So now it is nothing. So you have to use a general formula for the rate constant at any temperature, and that is K at any temperature T is equal to 2.22 into del delta 0 minus del delta. Okay. So del delta 0 is the chemical shift difference at the slow at the slow exchange regime, and del delta is I have already given. So this is your del delta. So this is nothing but 2.22 into del delta 0 we have found out is 42.5 minus 34. Per second, and if you do that, it comes to be 18.9 per second. Okay. Okay. So you can see that here because the peaks have not yet merged. Okay. So these the peaks merge when the rate constant is 94.35 per second. But still it is intermediate. It is just going from the slow regime to the intermediate regime. It is in between. So that's why it is around 19 per second. Okay. Now question C. Suppose you are now using a 400 megahertz instrument. Okay. Now we change the machine from 250 to 400 megahertz. Okay. The same NMR, same sample. Okay. At what value of K will the proton signals coalesce? Okay, so you have to find again the and will okay. Let us see K. We know that 2.22 into del delta 0 is nothing but the chemical shift value difference. Okay, and that values were 35.2. So those values were what was the chemical shift values? 2.9, right? 2.91 minus 2.74, okay, into 400. Now we are using a 400 megahertz. So previously we were using, so this is the chemical shift in ppm, okay. So we'll put this as a ppm into hertz per ppm. So this ppm is coming from this, and this hertz per ppm is coming from this. Okay, and if you do that, you will get if you do the calculation, you will get 151 per second. See, compared to 400 megahertz now, you see 250 megahertz. Now that it has increased, okay, coalescence rate. So automatically it will require higher temperature, because rate constant is directly proportional to temperature. Okay, so that means it will require higher temperature. Okay, so it will require higher temperature. Okay. Now next question, at what values of K the 13C signals coalesce at 250 megahertz and 400 megahertz instrument? Okay, I think you should be able to do it. I have already shown you. You know the chemical shift difference of I've given. Now these are proton frequency. You have to convert to carbon frequency and then use a simple formula. So I will not do that. And then will this occur at higher or lower temperature than coalescence? Of course, it has to, because proton chemicals, carbon chemical shifts are quite far apart. Okay, so they will require further higher temperature. Okay, to reach that. Okay, so it will require higher temperature. If you solve it, you will get require higher temperature than 1H. Okay, so if you solve it. Now let us come to the third problem. The problem is, now I've shown you a molecule, the room temperature 100 megahertz proton NMR spectrum of ketone. Okay, it's a diketone. Okay, exhibit the following sharp signals. Okay, and you can see this is the, okay, so this is the 2.0 singlet. That integration, if you do it, corresponds to 5 proton. Then 2.2. This is corresponding to 1 hydrogen. Then 3.7, that is corresponding to 0.16 hydrogen. Okay, and 5.7, 1.7 hydrogen. Okay, and you have the 1 hydrogen broad peak. Sometimes broad peaks are difficult to integrate. Okay, and this is the, okay, now explain why this happens. Okay, and what is the approximate enol content at room temperature. So now why it happens is simple. These diketones, they undergo a keto enol and they are temperature dependent. Okay, so now let us see question. So explain why this happens. Okay, so you should be able to tell why this happens. So there is a ketoenol equilibrium. So there is a ketoenol equilibrium. That I have already shown you. We have the diketone, and then okay. So the signals delta is equal to 2.0 and delta is equal to 2.0. So delta is equal to 2.0, 5.7 and 15.3 are due to the enol form. Okay, you can see. Okay, see enol form, you will have a alkene proton. You can see it is there, alkene proton, and then you have these two methyl groups will become equivalent. Okay, so that is coming here because both are equally possible. Okay, and this is your the enolic hydrogen. You know the hydrogen bonded hydrogen comes much downfield. Okay, and these small peaks, this one and this one, they are due to the keto form, and you can see that their ratio will be 6:2. Okay, so that's why this is 1 proton integration, this is 0.16, and this is nothing, it tells. So what is the percentage of enol form? So from that integration itself, you can tell that there is a 16% enol, sorry, keto component. So automatically your remaining will be 84% will be your enol. So enol is the major form. Okay, so from the spectra, from the chemical shift, you should be able to tell. Okay, when the temperature is raised, which signals will collapse? Okay, so you can see that these methyl groups will become equivalent. Okay, you see their chemical shifts. So you will see that delta at 2.0 and and delta 2.2 will coalesce. Okay. Similarly, all these protons, this and the OH, they are coming. Their origin is from the same proton. The origin is same. Okay, so their origin is same. So delta at this comes at 3.7, delta 5.7, and delta 15.2. They will coalesce. Okay, so you will have two groups of protons. If you go to very high temperature, you will see only two peaks. Now these two peaks, you have to now find out what will be their relative chemical shift values. You can find out. Okay, because if let us assume there is no change in the ketoenol content, you will be able to tell 84% is enol content, 16% of keto, and you have the peaks here. So this will have a contribution of 86%. This will have a contribution of 84%. This is 60%. Okay. Similarly, you will have all these things. Okay. So and you can find out. So out of that, you will have this. This will have 16% contribution, whereas these will have contribution of 84%. This can be 84%, this can be 84%. Okay, and you can find out. Sorry, this and this combined will be 84%. Okay, whereas this will be 16%. Okay, so you can find out. Now, between two groups, which groups will coalesce fast with increasing temperature and explain? So you can see the del delta for this group is equal to 0.2 ppm only. Okay, whereas here, if you see the del delta 0 max, which starts from is equal to 15.2 minus 3.7. That is the highest peak, and the lowest ppm is 3.7. Automatically, where the del delta will be more, that will require higher temperature. Okay, you can explain them in terms of K coalescence. Okay. Now the last part. So these are the these type of problems are very frequently or it is easy to solve using this dynamic NMR or temperature dependent NMR analysis of NMR spectra. Okay. Now I talked about the absolute configuration using Moser esters. Okay. Okay. So let us see. If you remember the summary, that's why I have summary. If you take the R Moser acid, okay, and if you make the ester with alcohol, this is your with S Moser, and this is your R Moser acid. Okay. Now this del delta SR is the chemical shift between the delta S, that means this ester, and minus this ester for a particular group of proton. Okay. Now, if del delta SR is greater than 0, then the group will be opposite side of the MTPA. So if del delta SR, let us say this group. Okay. So this group, let us say del delta SR is positive. Okay. So that means the phenyl group will be opposite to this group. Okay, how do we know that? So this is the relation. So these two will be opposite to each other in opposite side. Okay, if del delta SR is less than 0, then this phenyl and this R1 will be at the same side. Okay, so we'll see one example. Let us see. So these are the problems. Let us see first this one. Okay. So now assume this one. So this is your phenyl ethyl alcohol. Okay, and we may convert it to ester with S-MTPA chloride. Okay, now I am telling that delta methyl is positive. That means delta methyl SR is greater than 0. That means this phenyl and methyl will be in the opposite side. Automatically, the R group has to be in the same. The phenyl group has this phenyl group from the alcohol has to be in the same side, and so automatically you can now correlate the configuration. So this is priority group 1, this is priority group 2, this is priority 3, and if you see this is clockwise. So this the absolute stereochemistry of the center is alcohol is R. Okay, clear? Suppose if this SR could have been less than 0, then methyl could have been this side. The phenyl could have been at the back side. Okay, very simple to remember. Now let us see. This is one more example. This is your this example. You see that delta SR for this group is negative, and this group is positive. So that means the methyl will be down. Okay, you see the methyl will be opposite to phenyl. Okay, I am taking the ester, the phenyl group methyl group will be positive, so it has to be away from the phenyl. And these groups are negative, so they will be same side of the phenyl. This is happening to the anisotropic effect of the phenyl. And again, you get the 1, 2, and 3. So again, this is also R. Okay. Okay. So this is the way it should be. Now you can similarly you can see for this also. So now for this, if you see this side is plus, this side is minus delta SR. So that means if you draw in this scheme, all these group will be the below. Okay, and these groups will be above. So here will be your alkyl chain, and here will be your acetylenic system. Now, if you see that the priority of the acetylenic carbon is more than this, so automatically this will be 1, 2, and 3. Again, this will also be R. Okay. Same way, if you do for the this molecule also, you will get R. Okay. Now, but if you see this one, so this one is see you have this side positive and this side negative. Okay. So if you see that, that means these groups, this group will be going the back side, So now, but if you see the pattern, see in all cases so far, in this case, this case, this case, and this case, we saw that the priority of this methyl group is 3. Okay, but in this case, this will not be 3. This will be priority because of this double bond, the priority changes. So automatically now this will be of S configuration. Clear? So RS configuration you cannot tell just like that. You have to see the priority of the group. Okay. Okay. Suppose if it is instead of methyl, this is chlorine. The chlorine priority will be O and it will be different. Still, if it is chlorine, still it will be like that. But let us say if you put acetylene there, or some other, let us say oxygen, OMe. Okay, it will change. Okay, so you have to see that, and that will decide what will be the absolute stereochemistry. So you can expect such kind of question in the exam. Okay. So if you have any doubt, you can ask me, or I will stop here. And I'll be giving you this assignment maybe by Wednesday, and that you have to submit it by 31st May. Okay.
All other assignments.
Yes. So I'll stop here. If you have any doubt, you can ask.
Also tell the all other assignments all. They can submit by 31st.
And all other assignments. Okay. Whatever assignments. Okay. All other assignments.
All the assignments you should submit by 31st of this month. Okay. After that, this assignment will not be entertained. So this is the last date for the submission of all the assignments is 31st May.
Okay.
Okay.
So after by Wednesday you will get it. I will try to give it tomorrow, but if it is not possible, day after tomorrow you will be getting the assignment. So if you have any doubt, you can ask me, or I'll stop here and close. So this is your last class for your part 1 of NMR spectroscopy, part A.
And exam is on 16th June.
Most probably your most probable date of your exam is 16th of June. Most probable date.
And registration possibly will start from next 2.
Okay, and registration will start soon. Okay. अच्छा ये प्रॉब्लम्स को शेयर कर दें ठीक है